Hi, so today we have this pen here, and we are going to be learning about sig figs and density. Just an FYI, I had recorded about 5 minutes into the video when the phone that I was using at the time cut off, so now I switched to a different phone, but I will gladly re-explain all the steps that I had written during my first take. So, first off, we're talking about sig figs, and sig figs is just short for significant figures, and a significant figure is just any number that has value, specifically in the context of science. So before we can do any of these, or before I guess these numbers here make sense, we should go over some of the rules. So now the rules of sig figs is that the first rule is that all non-zeros count. So as I had written here, this number 13.6, they're all non-zero numbers. So it's 1, 3, 6. So these would all count. So there would be 3 sig figs here. So just to kind of make that visible, that would be 3 sig figs. So you see if you have the number 1, 2, 3, etc. You just keep going down. Those will all be considered significant figures. Now, when it comes to zeros, the zeros depend on their placement and whether there's a decimal. So in this example, we have 3.0. Now, like we said, it depends on their placement. See, it is behind the decimal, so it will be sig fig, and it says whether there's a decimal. So first we have to see if there's a decimal there, and the 0, and it has to be after a non-zero number. So this 3.0 equals 2 sig figs. But now we have the opposite, where we have the decimal, but it comes before it. So we have 0.0000000, keep on going, 4, 5. None of these zeros are significant because they all come before our two actual significant figures, 4, 5. So we only have 2 sig figs. So now, let's move that over here. Now, as you can see, the answer is already here, but I still want to just explain so that make sure you know them. So we have 0.00546. The decimal point is there, but these two zeros come before the 546, so there's only 3 significant figures. Then we have 1600 or 1600. Now, these zeros do not count because there's no decimal point. Had there been a decimal point between the 1 and the 6, then we would have 4. But since there isn't, there's only 2 significant figures, the 1 and the 6. Next, we have 2.300. Since there is a decimal point, and they're trailing zeros, which is the term that we'll use, there are 4 significant figures, 1, 2, 3, 4. And then 2.54 times 10 to the power 9 has 3 significant figures because we have this 1, 2, and 3 significant figures. Now, we're going to move over to now using sig figs when we're doing actual math problems. So here we have 5.71 plus 6.384 plus 11.5. Now, we're going to go and move it up here, and so here we have them written out. And when you're adding, you want to line up the decimal point. So we have the 6.384, and then the 5.71, and the 11.5. Now when you line them up, you want to have them lined up, and there's an operation here. You need to know your operation and your rule. When you're adding, your rule is the least precise sig fig. So when we move back up here, we have 11.5. The 11.5 is the least precise. So we would draw the line here. Let me write this, it's actually more accurate. So we would just have 13.5. But since this 9 is here, that's going to round up to 6, where we get 13.6. Now, just the rule of thumb is when figuring out how many sig figs for operations. When it comes to the operations of adding and subtracting, you're always going to do the least precise. Now, if we're doing multiplication and division, here's going to be the least number of sig figs. And that's one thing that students can get confused with, is assuming that everything, all 4 operations, are just going to be least number. No, that's not the case. It's going to be least precise for addition and subtraction, and the least number of sig figs for multiplication and division. So now let's move to one that has multiple steps. So our first operation here, so I'll just write O to save space, is going to be subtraction for step 1, right? Subtraction, okay? And then our rule, if we go back to our little chart right here, least precise. All right, we'll write that, least precise. So we will move up here and we'll put 12.32 minus 12.22. And just like we did here with the addition, you want to line up your decimal points, because it's a lot better. Actually, it's very encouraged that you do addition and subtraction by hand. That way you don't risk your calculator giving you the wrong placement or the wrong amount of sig figs. So you have 3 minus 2, which is 1, and then 0 and 0. So here we have 0.10. So we have 2 sig figs right there. So now we have 0.10 divided by 3.97. Now if I go and here, if I get this, just go 0.1 divided by 3.9, sorry, what is it? Okay, 0.1 divided into 3.97, we should get this number. So, looking at it, we should get, well, let's write equals here, 0.02518892. But we need it in 2 significant figures. Since we're dividing, go back here, the least number of sig figs. So our answer would be 0.025. That would be our answer. Now, moving down to density. Our formula for density is P equals M over V. And our unit for density is going to be grams per milliliter. Now it's important that you always remember to put your units at the end, because in science, if you just write 9.8, what we could be talking like meters per second squared, like for gravity, or we could be talking, if you just put 3.2, is it what? Is it grams, is it milliliters, kilometers, miles? It could be anything, right? So we want to make sure that we have the units. So let's look at this question here. A block of aluminum occupies a volume of 15.0 milliliters and weighs 40.5 grams. What is its density? So this question is pretty self-explanatory. So we'll write our equation or formula again. So P equals M over V, and then all we do is plug in. So if P equals our mass, it's 40.5 grams, divided by the volume, which we're given here is 15.0 milliliters. And if I get the calculator really quickly, 40.5 divided into 15.0 should get us the answer of 2.70 grams per milliliter. Okay. Then finally, we have this question. A plastic ball has a volume of 12.5 milliliters and weighs 1.36 kilograms. What is the ball's density? Now, something that we notice here is you want to read the units to make sure that we don't have to convert anything. But as we can see here, this is not in grams, this is in kilograms. So we're going to have to actually do dimensional analysis to change the 1.36 kilograms to grams. So what we're going to do is we're going to bring this down. Now we have 1.36 kilograms multiply is going to be 1 kilogram is going to be 1 times 10 to the third power. This is 1, 2, 3. It's going to equal 1,360 grams. Now we're not done. All we've done is just change this to the correct unit. We still need to plug this into our density formula. So now we have P equals M over V, and now we can plug in our mass here, which is 1,360 grams, over our volume, which was 12.5 milliliters. Oh, and I'm sorry, when doing the dimensional analysis, you want to put the same units here on the denominator so that these cancel out and you can just multiply across. So back to this. Now we have 1,360 divided by 12.5, which gives us the answer 108.8. But going back to our formula here, since we just did division, we want the least number of sig figs. So 12.5 is less. So we'd only do 1.8, which rounds to 1.9 grams per milliliter. And that is your answer. And now you've learned how to not only know how many significant figures is in a number, but you can also do operations, multiple step operations, and you've also learned about density and dimensional analysis.